we are going to do 3 hours on the board. I still owe you about 1 hour of what is remaining from reinforcement learning. So we've seen Bellman's optimality principle, but we haven't seen any learning so far. So I will show you basically two standard approaches that are used for reinforcement learning, and then I will show you at least the beginning of what I planned to show, basically how to do learning on non-Euclidean domains, and specifically on graphs and on manifolds. So there will be slightly more evolved mathematics, I would say. So far we've been using elementary tools. There will be slightly more complicated tools. Basically we'll lose some of the structures that we had in Euclidean domains. I will make it as elementary as possible. So just as a reminder, let me remind you what we did last time, and I will start with Bellman's equation. So basically, we are talking about finding optimal policies, right? And we translated the problem of finding optimal policies into the problem of finding optimal value functions, either state value or action value. Let me write it in terms of the Q function, the action value function. So an optimal Q, remember that QSA was, so QSA, the value function was giving me the expected return, basically a discounted return of a policy. Specifically Q, this action value function, gives the expected return if we start with state S, execute action A, and then continue according to the policy. Okay? And I'm writing Q star, meaning that basically I'm working with suboptimal policy. We've seen last time that there might be more than one optimal policy, but there is at least one deterministic policy that gives this optimal value function. And there might be many policies that give the same optimal value of the value function. Okay, so basically Bellman's equation tells me that this should be equal to the immediate reward that I receive by performing action A with state S, plus gamma. Gamma was the discount factor, sum over S running S prime, because S is given. S prime running over the states. Okay, this was the transition probability, right? And then basically I'm taking maximum over A prime over all possible actions A prime, Q star from S prime to A prime. Okay, so this was Bellman's equation, and a policy, a value function that satisfies this equation is guaranteed to be optimal. And then basically once we have this optimal value function, we can easily derive a deterministic optimal policy. So this policy will be pi star. It tells us basically, remember that the policy, we can think of policy as conditional probability distribution, right? It gives us the probability of making an action A when we are found at state S, right? So deterministic, it means that this will be a singleton distribution. It will be equal to probability 1 if A is exactly the arg maximum of Q star. And 0 otherwise. Okay? So basically this was Bellman's equation. It tells us a property that the optimal value function has to satisfy, and once we have this optimal value function, we can immediately find the optimal policy. Essentially the optimal policy is what we care about, because we need to know how the agent should behave, right? Because the policy describes the behavior of the agent. Now I told you also that we can actually solve this equation by doing fixed point iteration. So we start with some arbitrary q and just apply this, basically just apply a fixed point iteration. So we call this the Bellman operator. We apply the Bellman operator again and again and again. And as a result, it is quite easy to show convergence to an optimal value function. Okay, we've seen this monotonically increasing sequence of value functions. It is upper bounded, so we can show convergence. However, this is totally impractical. So basically, this fixed point iteration is called dynamic programming. You usually think of dynamic programming probably by using the metaphor of Dijkstra's algorithm for finding the distances in graphs, or maybe Viterbi algorithm for I don't know, for doing the hidden Markov modeling. Basically, all these cases are particular cases where we can do a single pass algorithm. But usually, dynamic programming requires this kind of fixed point iterations. And it is related, the physical interpretation of dynamic programming is related to what is called Hamilton-Jacobi equations. There is a lot to be told about this, but we don't have time. Okay? But the point here is that this is totally impractical if our state or our action space is very big. So, for example, if I showed you examples of Atari games, I think, last time. So in Atari games, the state would be the values of all the pixels we see on the game screen. So it's a huge state space. So many different pictures the game can show to us, and obviously we could, in theory, try solving this, but it would would require basically almost infinite amount of memory. So the solution to this problem, to make it practical, is actually instead of doing dynamic programming on this Q and then using Q to define the optimal policy, we could try approximating Q by some parametric function. Okay, and at every point we say parametric function, we think of a neural network, right? At least in this context. So basically, we put a neural network that will approximate this. Okay, and then we learn its parameters. So I'll show you in a minute how to learn this. And basically, these ideas have been in optimal control for probably several decades, probably starting from the 80s or the 90s. But the big difference between optimal control and what in the learning literature is called reinforcement learning, basically doing this approximation is called reinforcement learning. In optimal control, we usually assume that we know the MDP, the Markov decision process. So we know this term, we know this term. Okay? And then given a very well-known set of rules of the game, the environment, and basically how it pays off when we act upon it, give me the optimal control policy. Okay? Now, in the reinforcement learning, on the other hand, the typical setting is that we don't know the MVP. We don't know the rules of the game. We discover them together with the optimal policy. So basically, we don't know these. We might have examples of basically of our observations of the environment as a result of our actions, and as a result, we can learn the MVP together with the optimal policy, or together with the optimal value function. So basically, once we have the value function, we have the optimal policy. Okay? So this is what we are going to do, and this approach is called value-based learning, or Q learning. Basically, we are going to replace Q by some approximator. So we have a neural network, let's call it Q theta, that will approximate Q star. And theta are the parameters, and this could be a very complicated neural network. Okay? Now, what is typically done, so essentially Q receives the state as the input and the action as the input, and it gives us the probability of, or the vector, not the probability, the value of that action given the state. But in our context, usually the state, the size of the possible, the number of the possible states is huge. The number of possible actions is usually small. For example, if I'm playing a game, let's say Pac-Man, I can go left, right, up, down. So I have 4 possible actions. So the way I could better represent this function, I could let's say, I could represent it like this. So Q theta, let me write it like this. So Q star, I can think of Q star of performing action A, let me write it like this. From state S, I'm performing action A1 until some action AN. Let's say I have N possible actions. Okay, so I can think of this as a vector of values for every possible action at every state. Okay, so now I have a function that is only a function of the state. Okay, it represents exactly the same thing, but just in a different light. So I will think of Q theta as a vector valued function of the state. And the dimension of this vector will be according to the number of possible actions, so the cardinality of the space A. Okay? So basically it is a vector valued function, it is Q theta as A1 till Q theta as A. Okay, vector valued function. So I'm going to learn this parametric function, this neural network, that tells me the value of all the possible actions given the state S. And the state S will be a high dimensional input. Okay, so basically now our goal is to learn a function Q. Now we know what it should satisfy. We have a supervised learning set. Our function Q theta has to satisfy the Bellman's equation, right? So of course it will never satisfy it exactly because it's an approximation. So let's satisfy it, let's say, in the least square sense. So I have some target. I would like Q theta to be as close as possible in the L2 sense to some target y. Okay, so I will define a loss function L theta, which will be y minus Q theta. So of course it's expectation, right? It's the expected loss over S and A, expected loss over S and A, Q theta. I will write Q theta as SA, but remember that we are in practice representing this as a vector valued function. Okay? So I would like to minimize this loss with respect to theta. Of course, this amounts to doing supervised learning on the neural network Q, right? It's a regression problem, essentially. Now, where will the y come from? Yes?
After you perform an action, you get a state. And with the state, you can know the models, so your approximation of your Q.
Well, so what I can do, so I will just take, I can take this immediate reward plus what I have in the right hand side, in the second term of Bellman's equation, right? Now the problem is that the right hand side, the second term also depends on theta. So I will freeze that theta to be the current value of the parameters, and we'll of course do a gradient step, gradient ascent step on just on this. So y will not depend on theta; it will be constant with theta, and y will be given. So let's distinguish between two cases. So if remember we had this notation of terminal and non-terminal states. So if I'm currently I basically I have what I call experiences. I have these collections of current state, action, reward that I received, and the next state. Okay? So basically, when I'm playing a game, I have a trajectory that can be decomposed into such tuples, right? And we call this tuple an experience. Okay? So it's basically it's the basic unit of a game. It's one move in a game. So I can try playing these experiences. So in this experience, I had some state. I had some state S, some initial state S. I performed some action A. I was rewarded the reward T. Okay, and then I landed in some next state ST. So So if I landed at a terminal state, basically I'm done, right? So the reward I'm going to get for this move is exactly RT plus 1. So it is RT plus 1 if ST plus 1 is terminal. So the game is over, and this is the reward I received for making this move. Okay? Now if ST is not terminal, then I have this second term in the Bellman's equation that I need to account for. So it will be RT plus 1 plus this second term. Okay? So first of all, the second term is discounted by the factor gamma, and then it has maximum over the Q function that is also averaged over the states S, averaged with the transition probabilities of the MDP. Okay? Now the issue is that I would love to write this second term, but I don't know the transition probabilities. The MDP, at least in our setting, is latent. I don't know what are the transition probabilities yet. I will discover them implicitly as I learn. So basically what I'm going to do, I'm going just to write the maximum. I will not do the averaging over S prime. I have no way to do this averaging over S prime. But remember that we are going to do this learning on many mini batches of this form. Okay? I will tell a few words about how exactly to create these mini batches. But because we are going to do gradient steps on many mini batches, this weighting by the transition probability will occur automatically, right? Because we are doing averaging anyway. So this averaging will appear. Transitions that happen more frequently will appear more frequently in the mini batch. So essentially, I'm just ignoring this averaging, and I will write gamma max over 8 prime Q theta S 8 prime. And it should be, of course, it should be S T. Okay? So I'm taking this, basically this greedy step. I'm maximizing Q theta. Now, remember that we wanted Y to be independent of theta. Currently, the way it is written, it depends on theta. So let me write here theta minus to indicate that we are freezing theta. For the purpose of computing Y, we are freezing theta at its current value, and then when we are doing a gradient iteration, Y is constant. Okay? Okay, so basically, once we have defined our supervised learning strategy, we can just do learning, right? We play many games. We play entire episodes of games. We always take these kind of greedy actions. We try to minimize our current approximation of the value function. We encounter new experiences, and we do updates of the parameters theta according to these gradient steps. Yeah. Question there? Yes? No?
Shouldn't you perform your actions in such a case manner?
Okay, so I will say two things about this, but in a minute. Okay? Yes.
How can we expect that Q will converge to its true value, since there are so many states? So it's practically impossible to expect that we will visit every state. So practically P will never converge, and so how can we expect that Q will converge?
Well, so this is the difference between reinforcement learning and optimal control. In optimal control, you really care that every trajectory in this state space will give you, basically, that your behavior will respond well to every situation that you encounter in this control program. In reinforcement learning, essentially, those very infrequent trajectories might give completely, basically, if you now encounter a situation that you've never seen before, you might produce practically random behavior, right? So, but since it's very infrequent, it will impact your expected return very mildly. Okay, but you might produce completely wrong results. For example, if you are controlling a plane, I would say that it would be a very bad idea to crash this plane because you haven't seen a certain situation. If you're playing a game, I don't know, a computer game, then well, once in a while you will.
Every state is as infrequent as any other state because there are so many states. So you
Sure, but
the
don't-
optimal queue only for a tiny fraction of
Yeah,
the
but
states.
don't look at specific states. Probably first of all you should look at state action pairs, right? And
Yeah,
then
but
basically
actions are,
trajectories.
the space of action is very small.
Yes.
So you will discover the true queue only for a tiny fraction of states.
Sure, but
And, it will be
but-
practical for every other scenario you will encounter.
so basically, first of all these are valid constraints, right? But for example, if you are playing a video game, right? So your state is an array of pixels that you see on the screen. If you build, let's say, convolutional neural network that first processes that thing and extracts just some relevant features and encodes them in a sufficiently low-dimensional feature vector. Like, let's say you have some bricks that you break with a bow. So you should probably care where the bow is located, where the racket is located, and roughly what is the configuration of the brick, right? So you don't need all the pixels for that. So the way you construct your network queue will take care of reducing this number of dimensions. So basically you have many possible configurations of pixels on the screen that more or less mean the same. Okay, so it's still a very, very big state space, but not such a huge space that you start with. Okay, so I guess it's not a complete answer, but basically you will need to learn a lot. Basically you will need to crunch a lot of such training examples to get something useful. And of course you never get Q star. You get some of those. Okay? Yes.
Here you assume that the environment gives you a reward for each tuple, or at the end, the terminal state.
Okay, so basically we have what we call RSA, which is the immediate reward or instantaneous reward. Basically every transition from current state to next state gives you a reward. Okay? What you care about is the total return that is discounted with the discount factor gamma. Okay, so basically your instantaneous rewards are more important than rewards in 1000 moves, but the way you construct the MDP should be such, for example, if you're playing chess, let's say you get negative reward for every move, because you want to minimize the length of the game, duration of the game, and when you win you get a big positive reward. When you lose you get a very big negative reward. So of course that postponed reward counts a lot.
But you need to evaluate, for example, for chess, you need to evaluate every position and you need to evaluate how good is the position for black or white.
Well, that's why we have the value. So basically the position is the state. We have a very big state space.
And the environment is some chess bot that can evaluate and give you a reward for how well.
Well, so in case of chess, the reward is just -1 for every move. When you get to a terminal state, which is game over, then you give a reward, positive or negative, very big positive or negative number, according whether you won the game or lost the game. Right? And you want to maximize this discounted cumulative sequence of immediate rewards. Okay, so basically, how we learn this? So it would be very simple. So let's just start playing this game. We play entire episodes from the first state until we reach some terminal state, and I already told you that infinite games are not so practical for learning. We would like to actually to win or to lose at some point, and then to get rewards. The problem is that first of all, because our next move or next state or the next state and action pairs depend on what we played until the current point in time. Basically, we have very correlated training samples, right? If we just do gradient steps on every move that we do. And second, basically, we might get very biased examples. Because basically we are channeled into certain trajectories, right? Because we are moving according to the current Q function. It is inaccurate, it is biased to some maybe very bad policy. And then basically we are not seeing any other actions, any other state action pairs. Okay? So what improves this significantly in practice is the following idea, which is called experience replay. We are going to hold a big cache, big table, containing this set of tuples. Okay? So what we are still going to play episodes continuously from the beginning until the end. At every time when we are playing the episode, we are selecting this greedy policy. In a second, I will add some modification to this rule. So we are playing this greedy policy according to the current estimate of the Q value. It might be very bad initially. And we generate these experience tuples. We add them to the cache. Okay? Of course, if they exist in the cache, we don't add anything. And then we do gradient steps on mini batches randomly drawn from the cache. So we don't do updates, basically we don't do stochastic gradient updates on what we are currently playing. We are randomly selecting these tuples from the cache. Okay? And of course, the y is generated every time x novo because we have a different set of theta, different set of parameters. Okay? Of course, y is generated on the fly. The examples are taken from the cache, and we are playing a real game against a simulated environment. So we are adding new experiences to the cache. And this is called experience replay. And this way, we are less biased to the current actions that we are performing in the game. Okay? So this is a very useful strategy to make this algorithm actually converge to something useful. Yes?
Can you repeat please the reason for randomizing the experience, like the episodes?
Well, let's say your Q function is so bad that you are always pressing the left button in your Pac-Man game. So you won't see anything else except that very narrow set of trajectories in the game space, right? So basically the way you're going to learn your Q function will never basically you're not going to learn anything useful for any other state action pairs because many of the trajectories in that space are inaccessible in the way you learn, right? So you're extremely biased to that specific behavior, and that specific behavior is very bad. Okay. Now, what you could do, and this is a kind of a trade-off between exploration and exploitation. So basically, on one hand, you would like to exploit your knowledge that you accumulated so far by taking this greedy action based on the current value of the Q function. However, in this way, you might be unable to explore the consequence of other actions that you have never encountered so far. So basically, what is typical to do basically to balance between exploration and exploitation, you want to explore new actions. So with some small probability epsilon, you're going to take. So basically, you toss a coin which falls on one side with probability epsilon, and if it falls on this side, you just take a uniformly distributed action over the space of actions. So you take a random action, and you try this action. This is basically exploration. You explore the space of possibility, and with a probability of 1 minus epsilon, you do the greedy ones. Okay, and this also helps to discover something that you might otherwise be able to discover. Okay? Any questions? So this is a very simple and standard value-based learning strategy. It's extremely powerful. It can actually play real sophisticated games. The disadvantage is that it might still be a very, very complex function to learn. It depends on the very high-dimensional input. It might have, especially if you have many actions, it might be quite a complicated map between S and A to the value function. In some cases, it would be much easier to learn the policy itself. Basically, this function pi A given S. In many cases, it might be easier to approximate this function rather than approximating Q of SA. Okay? And basically, moving from approximating Q to approximating pi gives rise to a set of methods that are called policy-based learning. In policy-based learning, we are interested in learning directly pi. So instead of having this pi star, which is our optimal policy, we again put some parametric function. So think of it as a neural network. We have a parametric function pi theta that approximates pi star. Okay? And in case we are learning a deterministic policy, we can just again represent pi theta just as a function of s and give, or essentially even in the stochastic case as well, given s, we can just produce a vector of probabilities associated with each of the actions A. Okay? So again, it can be a vector valued function, pi theta of s. So it will be a vector of pi theta A1 given s, and pi theta AN given s. Okay? Now, what would be the loss? What would be a meaningful loss in this case? So we are optimizing the policy, right? So let's write some loss. I will use a different letter. Let's call it J theta. Okay, and I would like to define some loss. And of course, I'm interested in the total return, right? In the expected total return that I'm going to get if I play according to this policy pi theta. Okay, so let me write it as the expectation over G. We call this total return G. I will write it G of tau. Tau will be a trajectory that my policy produces, right? So I have many trajectories. Basically, trajectories are just sequences of this type, right? It is S, A, R, and then again, next state, next action, next reward, until I reach a terminal state. So basically, each episode, each game episode, from the beginning state until the last terminal state will be a trajectory. And of course, this is conditioned. This is a conditional expectation given my policy pi theta. Okay? And let's write it explicitly. It will be the expectation of the sum t greater or equal to 0, gamma t plus 1, r t plus 1, given pi theta. Okay? Should be, I think we wrote gamma, right? And gamma. So the first weight will be 1. Okay, and again, tau is just a trajectory of this type. Tau is the sequence ST1, t greater or equal to 0. Okay? So let's write, we have basically this expectation, let's write the probability of each trajectory explicitly. So let me write it this way. Let me write this J. I will write it I will write this expectation explicitly. It will be let me write it like this. It will be an integral d tau pi tau given theta of g tau. Okay? Let me write it this way. And p tau given theta is exactly the probability density, or the probability distribution, the conditional probability distribution of each trajectory tau of this form, given the current parameters of the policy. Okay? Okay, so let's compute Pt given tau explicitly, this conditional probability. So we have a Markovian process, right? So it's really easy to compute probabilities of a Markovian process. So essentially, we would like to compute the probability that basically this total probability of this sequence S T A T R T plus 1 given theta. Okay? So how do we compute the probability of a Markovian process? First of all, we write some probability of the state S0. Okay? Some initial distribution of the states. And then we have for T, basically we have a product of probabilities, T greater or equal than 0. We have basically a product of transition probabilities times the policy, right? The policy is the probability of taking a certain action. So this is pi theta, the probability. So I start with state S0, okay? Now the probability of taking an action, A1. Okay, so initially it will be probability of taking an action A0 given S0. Okay, so of course this runs for other times. So again, I'm starting at S0. The probability of making an action that I observe A0 from the state S0 is given by this probability distribution, right? We call it policy. And we multiply this by the transition probability of the MVP of transitioning to state. So I made an action AT from state ST, okay? And basically this is the probability for this. What is the probability of transitioning to ST plus 1 as consequence of this action? Okay? And this is the transition probability of the MDP. Okay? Then I'm in state S1, and again I ask myself what is the probability of making the action A1 from state S1, and the probability times the probability of transitioning to state S2 from the state S1 under action A1. Okay? And then I do it until I reach my terminus. Okay? So basically we wrote our loss, let me write it again, we wrote our loss in the form of this integral with this probability. Okay? This is our expectation. G is our expected return. So let's take the gradient of this with respect to theta, right? We just need to maximize it. So we'll make gradient ascent steps on this loss J, okay? And we're done. Let's just maximize this with respect to theta. So I'm interested in computing the gradient of this J with respect to theta. Okay? So let's take the gradient explicitly. Of course, we have this linear operator that defines the integration. Only the term P depends on theta. G doesn't depend on theta. So we have the gradient of P with respect to theta. And apparently this is intractable, right? Doesn't sound like something we can efficiently evaluate. Maybe we can evaluate it by something, but really sounds intractable. But let's do the following trick. I would like to, so under the integral, I'm multiplying everything by P given theta and divide everything by P given theta. Okay, so basically, I will have this P given theta, gradient of P given theta over P given theta, sorry, G, which doesn't depend on theta. Okay? Now when you see something that looks like derivative of f over f, what can you see? Of the log, right? So let's write it explicitly. We have the integral of P given theta, gradient of the log of P given theta, times G tau d tau. Okay? And this basically this is an expectation, right? So we we turned this apparently intractable gradient of the expectation into the expectation of the gradient of the log. Okay? Nice trick. So let's write it explicitly. This will be the expectation over tau. This expectation over tau, of course, distributed. So let me write it explicitly. Distributed with p tau given theta. It depends on theta. Of what is written under the integral, basically the gradient of the log of pt given theta, g tau. Okay, so this already looks tractable. Let's do a side calculation. What is exactly this log of p tau given theta? So let's substitute this formula. Under the log, of course, it will become log of basically a sum of logs, right? So we have log p as 0 plus sum over t log pi theta at given st plus sum over t of log p st plus 1 given st at. Okay? And pay attention that out of these three terms, two terms are constant in theta. Just the second term depends on theta. Okay? Basically only this term remains in the gradient. So we can write this. Let's substitute this explicitly. So we have an expectation. We have an expectation over tau of g tau. We have the gradient. Let's write it as the sum, right? The sum over t greater or equal than 0. The gradient of log pi theta at given s. Okay? This already seems like a tractable expression, right? So of course we could do expectation over our trajectories, over our episodes tau, but since we are doing stochastic gradient iterations anyway, I can remove the expectation and basically compute a gradient on a single sample or a single mini batch, doesn't matter. And then basically by doing such steps, we are going to average the gradients. So if I do a single stochastic gradient iteration, what I have instead will be the gradient of j of our loss function is equal to g tau sum over t gradient of log pi tau at given s. Okay. So whenever I'm playing an episode, pay attention that this is the gradient on which I'm going to do the gradient steps. Now look what I get. I get the sum of these gradients. So basically you see for every trajectory, so I'm drawing from my mini batch a trajectory and doing a gradient step. And this gradient step is going to update the weights in such a way that the policy will somehow change probabilities of acting on certain trajectories. So if I have a trajectory tau that gave me a very high reward, okay, I'm going to update the parameters in such a way that it will increase the reward of such action, right? So it basically will promote the actions that gave me high reward. And if I go to a trajectory with a low reward, then I'm going to update my parameters in such a way that the policy will make these actions less probable. Okay? So I'm going to boost those trajectories that have high reward. Okay?
But it's not just taking an action, it's taking an action when you're in a certain state.
Of course. So that's why I'm talking about trajectories, right? So basically along the trajectory, I have a sequence of actions that I took from a certain sequence of states, right? So I will update my weights in such a way that it will increase the probability of those combinations of states and actions, right? I would like it to be more probable because I'm doing everything under the expectation. So basically, it looks a little bit dramatic that that I'm taking the total reward, basically the total return of the entire trajectory that might be very long, in order to make a decision about these instantaneous state and action pairs, right? So maybe what I should be doing instead, maybe I should be taking just, instead of G tau, which basically starts from t0 until infinity, let's maybe start from just the current time, right? So instead of writing it this way, let's write t going from 0 to infinity, another sum. Basically, instead of g tau, I'm going to start t prime from t, okay? My discount will be gamma to the power t prime minus t. Okay, return at t prime plus 1. Okay, so initially I just started unconditionally from t equals 0. Okay, and this counts only from this counts only returns that I will be receiving from this time forward in time. Okay, and of course I'm multiplying this by the gradient. Okay, so I can do this calculation of the gradient instead. It will give a slightly better weighting, but still this takes the absolute value of the return that I'm going to see too seriously. Actually, I don't really care about the actual value of the return. I only care about whether it will be better or not than some expected return, right? So essentially, I would like to not to measure this value and use it to weigh the gradients, but compare it to some baseline. Compare it to some baseline. I'll denote it by the function of S. So some baseline that I would be expecting to get the return that I'm going to I expect to get from basically if I found that state ST. And when initially policy-based learning was proposed, this kind of baseline estimation was done by just running some kind of moving average. So it's a very naive way of approximating the baseline. But what would be really the best baseline you can think of? Or what basically how should I weight these terms? So basically this is what I'm expecting to receive when I found the state ST. Okay? And this is what I'm expecting to receive when I'm acting by action AT from state ST. Right? So what should I write ideally in these parentheses? I would like to write the difference between the Q function and the V function, right? The action value function and the state value function. So instead of writing this, I would like to write Q ST AT minus V ST. Right? So this is called this is usually called the advantage function. So basically it's the difference between taking a specific action AT at state S, basically the difference in return between just the expected return over all possible actions that I can take as state. Okay? So basically I would like to work with gradients of this form. Okay? Now if I knew the value functions, of course I could just substitute the value function, or let's call it if it's called the advantage function, let's call it alpha STA. Okay, this is the advantage function. Okay? If I knew this advantage function, the difference of the Q value function and the V value function, I could just do learning of the policy pi, of the parameters theta of the policy, using gradient ascent on these with these gradient terms. The problem is that I don't know the value function, right? If I knew the value function, I could immediately derive the policy function, as we did with Q learning. Okay? So what could I do?
Learn it together with the policy.
Exactly. So basically, I will learn the advantage function. So I don't have the advantage function. I will approximate it by some alpha with parameter phi. Okay. I should have written here stat. Right. This should be the optimal advantage function. But I don't know the optimal advantage function, so let me learn it together with the policy. So basically, I have two learnable pieces in this system. I have the policy that is parameterized by the parameters theta that I'm learning, and I have the advantage function, the value function essentially, alpha, also a neural network parameterized by another set of parameters phi, that I'm learning simultaneously. And this leads to a reinforcement learning strategy that is called actor critic. So I have basically two pieces that are learned simultaneously. I learn the actor, the behavior, the policy, and then I learn the advantage function, the critic, that tells me how well the actor behaves. Okay, so I'm trying to improve the policy, and I'm trying to improve the estimate of the quality of the behavior. Okay. So basically, this is a very common way of doing policy-based learning. Essentially, it is a combination of policy-based learning with Q-learning that we have seen before. We are learning more parameters, but it works really better. And these tricks were proposed in the recent years by people from DeepMind. They really applied it impressively to many types of games and other reinforcement learning settings. So this is one of the standard ways of doing policy grading, policy-based learning. Okay? Any questions? Okay, so if there are no questions, let's do a short break. So I would like, basically, by this we are finishing with reinforcement learning. You will see something in the tutorials as well. And I would like to switch gears and start talking about learning on non-Euclidean domains. So it's a kind of a more exotic type of learning. It requires slightly more elaborate math. But basically, in our age where we have a lot of graph value data or data on graphs like social networks, and so many other unstructured types of data that cannot be represented easily by a vector space, it is becoming increasingly important. So I think it is important to at least speak very briefly about this kind of learning session. Okay? So let's do it after the break. So basically, we have seen, just reminding you, we have seen quite a few learning scenarios so far, right? We've talked about supervised learning, we've talked about unsupervised learning, about reinforcement learning now, right? So basically, we also discussed different network architectures. But in all the settings that we have discussed so far, there was one maybe in most cases tacit assumption that our data come from some Euclidean geometry. Basically, we could represent our data as vectors. We could perform operations like U plus V on our data. right? We could construct convolutional neural networks. So in order to define convolution, remember that for convolution we needed to subtract one vector from another, right, to define translation. Okay? Now, when we think about other types of data, for example, like graphs, that arise in many domains of science and engineering. For example, think of a sensor network. We have some configuration of distributed sensors that are measuring some values. So we have a graph, maybe dynamically changing graph, on the vertices of which we define some time signal. Okay? So this is not a linear space anymore. We cannot really, for example, translate something, at least not trivially, from one region in the graph to another region of the graph. How exactly do we do this? There is no translation group that can act on the graph. Or if you think, for example, of geometric data, some range data, we acquire point cloud, or let's say a triangular mesh, like in computer graphics or in 3D vision, and we would like to, let's say, operate on it with a convolutional neural network. What exactly does it mean to do convolution on a non-Euclidean manifold? So let's try to extend our tools. So basically our main, most powerful tool was convolutional neural networks, right? So let's try to extend this notion to non-Euclidean domains. So I'm going to do it in 3 steps, and hopefully I will not lose you in the process. So first of all, I will remind you the notion of convolution. That was basically our main workhorse, our basic ingredient in the convolutional neural networks. And let's see the properties of convolution. Specifically, I would like to talk about spectral properties. So I will remind you or define, depending on your background, what is the Fourier transform. And using the Fourier transform, we will be able to give an alternative definition to convolution. So convolution was the application of a Toeplitz operator. We will define it in the spectrum as a product of Fourier transforms. Okay? And if you have never encountered the Fourier transform, well, this will be the first time we'll define it in a self-contained way. Now, then I will basically, because we want to talk about non-Euclidean domains, so let's define what a non-Euclidean domain is. I will define with 2 types of non-Euclidean domains. I will show you what an Riemannian manifold is, and then we'll see that a discrete representation of a Riemannian manifold is a weighted undirected graph. So I will show you how to do calculus on manifolds, something that in math is known as differential geometry. And we will see some kind of a difference operator type of generalization of these notions of gradient and divergence and Laplacian operators on manifolds. We will carry them to graphs in a very similar manner. Now, once we have the Laplacian, so my goal will be to construct the Laplacian operator. Once we have the Laplacian, I will show you how its eigendecomposition gives us a non-Euclidean analog of the Fourier transform. Okay? Now, while you cannot define convolution of the manifold or the graph, you can still define a product of Fourier transforms. And this will be our new definition of convolution that we will carry to non-Euclidean manifold or to graph, basically to general non-Euclidean domains. So we will lose some properties. We cannot talk about any shift invariance type of property, but still this will be a well-defined notion. It will be a useful notion. We will be able to construct convolutional neural networks, or at least non-Euclidean analogs of convolutional neural networks, learn them, and do basically cool stuff of analyzing data on non-Euclidean domains. Now, it is important to distinguish between 2 types of problems. We can think about problems where we would like to learn the properties of non-Euclidean domains versus learning properties of signals on non-Euclidean domains. So these are very different problems. So we have encountered essentially manifold learning, or basically discovering a non-Euclidean domain, when we talked about unsupervised learning, about autoencoders. So we were given some collection of points or some distribution in an embedding space, and we wanted to extract that manifold structure from which the data were generated. And what I'm going to talk about is rather a different problem, is how to do signal processing, or how to do learning on graphs, on manifolds. So we have some scalar or vector fields, on graphs or on manifolds, and we would like to do learning on them the same way we did in RD, in the Euclidean space. Okay? So this will be our goal. So let's start with convolution. Okay, so remember that our convolutional neural networks, the main ingredient of every layer is convolution. So convolution, I just remind you, we have a sequence, and let me now, so I always talked about time sequences, and I told you that we can easily extend time sequences to any domain, so let's be specific about it. I have a signal, x, it will be a scalar function. I will index it with n in z. So if d equals 1, think of it as a time series. D equals 2, this is an image, a discrete image, a sample image. D equals 3 is a volumetric image, and so on. Okay? Now I will write the convolution y equals the convolution of I have two such series, two such signals, discrete signals. The convolution of x with w at point n, and n again is a multi-index in ZB, is given by the sum, let's say for p, also in ZB, of w p x n minus p. Okay? This is convolution.
And what is n?
N is an index. It doesn't matter, it's a symmetrical function. It's a symmetric.
Thank you.
Okay? Yes.
So you don't require uniform sampling anymore?
It's a uniform. It's a Cartesian grid. Right? So it's a product. It's a product of. So it's a tuple with the integers, or the integer numbers. Right? So we have integer coordinates. These are indices. So of having just one time index, we have, let's say, two space indexes. But let's say pixel I and pixel j, two coordinates of the pixel. Okay? So this is convolution, and we said that convolution can represent any, well, in the signal processing literature, it's called shift invariant, linear shift invariant operator. So basically, any linear shift invariant operator can be represented as convolution with some function w, some signal w, that is called the impulse response, the green function, the kernel of this operator. Basically, these are different synonyms from different fields of science and engineering. The term shift invariant is terribly wrong. The correct mathematical term is translation equivariant. So basically, an invariant quantity would be something that composed with the action of the translation group remains the same, right? But what we have instead is a quantity that commutes with the action of the group. So this is called invariant, this is called equivariant. Now, we are not going to fix this abuse of terminology. So linear shift invariant systems is how they are called in all signal processing books. Okay? But just remember that this is the wrong term. So basically we have this function, we have this system, let's call it W, that acts on a signal x. It's a vector in some infinitely dimensional Hilbert space, usually called L2, that is represented by this convolution of W dx. Okay, so this is called a Toeplitz operator. Okay, let's call them Toeplitz operators instead of shift invariant operators. I think this is a better term. Okay.
Just writing this way instead of writing the convolution?
Well, it's basically an equivalent representation. So if you think of this, so if you think of x as a finitely dimensional vector, then W will be a Toeplitz matrix with basically all the diagonals will have the same number of the diagonals. Okay. Now, what is the action of a linear operator on a vector in general? So let's say you have a finitely dimensional vector, and you are multiplying it from the left by a matrix. So, question? So basically, you will have some rotation and scale. right? So the vector will rotate and the length will change. Now there will be a set of privileged directions in which only scaling happens and no rotation occurs. Okay? And these particular directions are called the eigenvectors of the linear operator. Okay? Now let's see how let's see the structure of the eigenvectors of Toeplitz operator. So let's take this Toeplitz operator, and I would like to define this family of functions. I will call them phi psi. Basically, psi is a parameter. It's a discrete signal. So let me write this variable n. This is the argument of the signal. I will define it as e to the power I 2 pi inner product between psi and n. Psi is a parameter in the space 0, 1 to the power d. D is the dimension of this domain. Of course, n belongs to z to the power d. Okay? So again, psi is a parameter. We'll call it frequency. And n is our, think of it as time parameter, time arguments, space argument, doesn't matter, depending on what this signal represents. Okay? And let's see how our operator manipulates this vector, this signal phi. Okay? So we have a convolution. It will be given by the convolution of this phi with w. W is the impulse response, the green function of
And
the
here
operator.
it's still multidimensional?
Pardon?
And here
N is d-dimensional, yeah. I'm assuming that n is d-dimensional. Okay? So you can think of it as a one-dimensional, but so then you don't need this inner product. We will just
Okay.
thank you. Okay, so let's write it explicitly. Let's basically write this convolution explicitly according to this definition. It will be sum over p, wp, and let's write it explicitly. E to the power I 2 pi psi transpose n minus pi. Now, because the exponent can be written as a product, basically the exponent of this difference can be written as the product of two exponents, the summation index is p, and the exponent in n doesn't depend on the summation variable, so let's take it outside. We have e to the power I 2 pi n, sum over p, wp e to the power I 2 pi minus I 2 pi C transpose P. Okay? Now, what is this? I'm missing, of course, psi transpose. Psi transpose.
is the vector that's going on.
This is exactly this vector, this signal phi c, right? So this is phi c. And now let's call this quantity, let's call it w hat function of c. Okay? So basically what we got is w hat function of c times phi c. So remember, we act with the linear operator w, think of it as a matrix, on this vector phi c, and we get some number times phi c. So how do we call such phi c? It's an eigenfunction, right? Or eigenvector of w. So basically this is an eigenvector, and this is the corresponding eigenvalue. Okay? Now pay attention that the eigenvalue, of course, by its definition, depends on w, right? What about the eigenvectors? The eigenvectors don't depend on w. So any Toeplitz operator will have the same eigenvectors. This is a very powerful property.
So because the two Toeplitz matrices are commutative.
Exactly. This is exactly. So basically, they can be jointly diagonalized, or they share the same eigenbasis because they commute. This is an if and only if. Okay. Okay. So let's just give it a name. So this quantity w hat of psi is called the Fourier. It's called the frequency response of the operator w, or it's called the Fourier transform of w. So basically, let me define an operator. I will call it f, an operator that will map signal. So basically it will be an object in this Hilbert space. This is basically the space of all square summable sequences indexed by a d-dimensional index to the space of square integrable functions on the domain 0, 1 to the power d. This is where psi lives. Okay? So basically this operator is called the Fourier transform. And it maps W to W hat. Okay? So this is again this is a sequence or a signal basically with a discrete index n, and this is a function of a continuous variable living in this space. Okay? So basically these are two different objects. Now the inverse transform will take us back from this capital L squared to lowercase L squared. Okay, so basically it will map W hat back to W. Okay? And I'm claiming that this inverse transform is given by inverse transform of W hat. It has to be a discrete signal, right? So it will be an integral over 0, 1 to the power d of W hat c e to the power, well, let me write it without e first. It will be phi c dx. Okay? So each of these objects is a time signal, right? It's a sequence with a discrete index. We are just multiplying it by some number and summing all these contributions. Okay? And it's very easy to check that this will be the inverse of the Fourier transform. So shall I do it, or is it obvious that this basically inverts the action of f? Okay, let's do it quick. So let's substitute W hat defined this way. Okay? Let me write it here. It's integral over 0, 1 to the power d of the sum Wt e to the power minus I twice pi C transpose P times e to the power I twice pi C transpose n. Okay? And n will be, so it will be basically f applied to W, then f inverse applied to it at point n. Okay, this is the value of this inverse. Okay, and I would like to show that this is exactly W. Okay, so this means that this definition actually inverts f. Okay, so basically what we have here. So what we have here is, let's switch the order of sum and integration. We have sum over P WP, integral over 0, 1 d, e to the power I 2 pi psi transpose, n minus p. I'm missing big psi here. Big psi. Okay? Now what we have is the integral, so basically what we have here is a periodic signal, right? Now the periodic signal with, pay attention, with an integer frequency, right? So it's 2 pi times an integer, okay? And I'm integrating it over the domain 0, 1 to the power d. So let's just for simplicity assume that d equals 1. I'm integrating a sine or a cosine, it's a complex exponential, over the interval into which an integer number of periods fit. Okay, what would be the answer? So for every peak, I have a negative dip of the same shape, right? So what would be the answer? 0, except
For the same.
Say for zero frequency, right? For zero frequency, I have a constant function, 1. So basically, the answer, the outcome of this integration is delta n minus p, Kronecker delta, right? So it is 1 if n equals p and 0 otherwise. Which means that these complex exponentials are orthogonal, right? Because what is written here is an inner product. So basically, I'm left with a sum over p, wp delta n minus p, which translates to w, right? So it's w. This is exactly what I wanted to prove, right? Because basically, this action of f and f inverse gives me w. Okay. Now let me write these operators in a slightly different form. So let me define an inner product on this space, an inner product between two sequences, two signals f and g, as simply the sum over p of fp gp complex conjugate. Okay. So if I'm writing it this way, the Fourier transform of w, so the Fourier transform of w at point psi is nothing but the inner product of w with phi psi. The minus sign in the exponential goes, basically it appears because of the complex conjugate, right? So if you substitute this into the inner product, you will have a complex conjugate will invert the sign of the phase of the exponential. Okay? And I can think, so this is an inner product on lowercase L2. And of course I can think of the inverse transform at point n as the inner product of w with phi n on this space.
With the integral now.
And of course the inner product will be the inner product between two functions on this domain will be the integral over this domain of f p, or let's call it f psi. F psi. Let's even put hats here just to keep consistent the representation. G hat complex conjugate of psi d. Okay? Now if you think of it this way, so I'm only missing, of course, here I need to put complex conjugate, right? Because in the integral I have the exponential, basically I have it with a plus sign, right? So if I want to plug it in the inner product, I need to plug it in with the complex conjugate in order to get the plus sign. Yes?
Isn't the inverse Fourier the inner product of w hat with?
W hat, of course. Right. It's W hat. Okay? The argument of the transform. Right? So basically, if you think of it this way and try thinking of it as a matrix, so you can see that F inverse is just the conjugate transpose of F. Okay? So basically the inverse is the conjugate transpose, it's the adjoint operator, and this property is called unitary, right? It's the generalization of rotation to the complex field. Okay? So basically, because the Fourier transform is a rotation, and the inverse transform is the inverse rotation, it preserves lengths and angles, right? So it means that an inner product between two signals in the original domain, in the standard basis essentially, and the Fourier domain will be the same, right? So basically, if I have f and g inner product on L squared, I have a certain inner product, it will be equal to the inner product of their Fourier transform. Okay? Okay? For every f and g. And this is called the Plancherel identity. And probably a more famous identity is derived when, in the particular case, when you substitute g equals f. So if you substitute g equals f, this inner product of f with itself becomes the norm squared of f, right? So basically, if I substitute g equals f, I have the norm squared of f on lowercase L2 equals to the L2 norm squared of f hat on this space. Okay, this is called the Parseval's identity. And again, this is just a direct manifestation of the fact that the Fourier transform is a unitary operator. So another way to view the Fourier transform is just the transformation of the basis, right? So I'm just changing the basis. I'm just changing the basis into not some arbitrary basis, but the eigenbasis of my operator. And by a lucky chance, or it's not a chance, it's a very powerful property, this eigenbasis is common to all Toeplitz operators. So I don't need to translate into a basis that is specific to a specific operator. Basically, all operators share the same eigenbasis. So this means that I can write my input sequence. So again, remember that the Fourier transform gives us essentially projections on the eigenfunction, eigenvectors of any Toeplitz operator, right? It projects our signal onto these functions. And the inverse operator allows us to reconstruct the signal again in the standard basis. So if I have some sequence x, I can write it as an integral of some coefficient times phi c dc. So basically, I'm writing my x as a linear combination of these basis vectors, right? So with a just small complication that I have a continuum of such basis vectors, right? Indexed by this variable psi. Okay? And what will be the coordinates of such a representation? Exactly the Fourier transform, right? These are coordinates of my vector psi in the new basis. Okay? Now, to get back, so this operation is called analysis, right? So basically, when I transform my x to x hat, this is performed by the Fourier transform, and this operation is called analysis. And the inverse operation is called synthesis. Basically, I reconstruct the signal back in the standard basis, and it is done by the inverse Fourier transform. Okay? So basically, this is the inverse transform, right? What I wrote, and this is the forward transform. Okay? So basically, computing these coefficients is analysis. It's computing those inner products, and basically computing this sum is called synthesis. Okay? So let's now substitute this representation as the input to our operator and apply convolution. Let's apply convolution to x. Okay? Now, in applying convolution to x, I will write convolution of this, basically with this representation in the eigenbasis. Now, convolution is a linear operation, right? It's a sum. So let's put it inside. Okay? Do you agree that it's the same, right? Now, what can you tell me about this quantity? I'm applying this Toeplitz operator, characterized by the impulse response W, by the filter W, to its basis functions, to its eigenfunctions, right? What will I get? I will get W hat psi times phi psi, right? Of course, it has to remain the same object. So it will remain phi psi scaled by some complex number that is given by the frequency response of W, by the Fourier transform of W at point psi. Okay? So basically what I got is the integral of 0, 1 d of this quantity x hat psi w hat psi times phi psi d psi. Now, what is this integral?
The transform of them into the
It's the inverse transform, right? It's the inverse transform of what? Of this pointwise product of x hat and w hat. Okay, so let's write it explicitly. This is the inverse Fourier transform of f x times f w. Okay? Or graphically, if you will, convolution in the standard basis becomes product in the Fourier basis. Okay? Now, it's not surprising. So think of it as matrices. I have a Toeplitz matrix. I'm writing it in its eigenbasis. Obviously, it becomes a diagonal operator, right? And applying a diagonal operator is just amounts to element-wise products, right? So essentially, the Fourier transform has this powerful property because it diagonalizes every shift invariant operator, every Toeplitz operator. It always diagonalizes all Toeplitz operators. So when we work in the frequency domain, in the Fourier domain, we are basically working with the diagonal representation of the linear operator. Okay. Now, because of this equivalence, you can think of this as an equivalent definition of the Toeplitz operator, right? So every Toeplitz operator can be described by its kernel W. Let's call the impulse response. So you give me an impulse response, and this creates your Toeplitz operator, or alternatively by a frequency response. Okay? So give me a function of psi, and I will compose you a Toeplitz operator again. This is an equivalent representation. Now, why is this so important? So first of all, this is a very powerful technique for analyzing linear systems, or basically linear translation equivariance systems. However, for our purpose, this will be even more important because when we switch to non-Euclidean domains, this will be undefined. We'll be unable to define convolution anymore. We will be unable to define a translation equivariant operator because there is no translation group acting on a graph, for example. There is no such a thing. However, we will still be able to define this. Okay? Now, because in the Euclidean domain these definitions are equivalent, we will just stick to this frequency-based definition as what we mean by convolution. Of course, it will lose some of its property. We will be unable to say that this is a translation equivariant operation, but it will still give us a meaningful way of defining filtering on a non-Euclidean domain. Okay? So basically, this is why I insist on making this definition explicit. Okay? Of course, there are many more properties of the Fourier transform. I think we'll stop here. So let's do our next step. So now we know how convolution works on Euclidean domains. Let's see what it is a non-Euclidean domain, and then see how to generalize convolution through the notion of the Fourier transform to non-Euclidean domains. Okay? And then once we have convolution, of course, we can create convolutional neural networks, and then it will be just mechanics. Okay, any questions? Okay, so let's start with, I would like to show you two constructions of non-Euclidean domains. One of them will be continuous, another one will be discrete. So let's start with the continuous construction, then the discrete construction will simply repeat the same steps in a discretized way. So let's start with the notion of a manifold. So a manifold is just an abstract definition of a surface, some generalization of the notion of a surface. So think of a surface, for example, of the Earth, or the boundary of any physical object. So basically, we define a manifold, a d-dimensional manifold, as a topological space that is locally homeomorphic to a Euclidean space of dimension d. So basically, we can find a homeomorphism. It's a continuous map with continuous inverse that maps an open surrounding of every point in the space to Rd. Okay? So let's say I have this surface. Manifold doesn't need to be necessarily visualized as a surface, but I can take a point, take some surrounding here, and map it to a Euclidean space. Okay? This Euclidean space, the d-dimensional Euclidean space, will be called a tangent space. So this point P on the manifold, let's call it M, I will associate it with PPM. This is the d-dimensional tangent space. So it is homeomorphic to Rd. Okay? So basically, to every point, I attach a linear space. Okay? And again, for a surface, for a two-dimensional surface embedded in R3, I can actually construct it by building a tangent plane. Okay? By basically taking a surface and applying basically a tangent plane to this surface. But the manifolds can be more abstract features. It's actually interesting that every manifold can be implemented as an embedded surface in a sufficiently high dimensional space. Okay, and then the disjoint union of these tangent spaces over P will be called the tangent bundle. So it's the collection of, so this is tangent space, and this is the tangent bundle. Okay, so it's basically the collection of all tangent spaces. Now, basically, what we would like to do with, yes, a question?
Tangent bundle is the collection of all tangent spaces of all the points on the manifold.
Exactly. Yes. But again, it's a disjoint union. So the resulting object is a set containing a collection of linear spaces, and not a collection of vectors, right? Now, each such linear space, we can think of it as a Euclidean space, right? So we can equip it with an inner product. So we'll define an inner product on the tangent space. At every point, it will be different inner product, of course. And this structure, under a small provision that it has to vary smoothly as function of P, and I will not define exactly what it means, this is called a Riemannian metric. Or simply a metric, and the term is very unfortunate because metric also means something else. You know, it's called a Riemannian metric, and basically it allows to locally measure angles and lengths. Okay, because this is what inner product does. Yes. Well, I can measure it. So basically, if I'm standing in the surrounding of a point, I can make a small step in. On the manifold, it will translate to a vector in the tangent space, and then I can measure the length of this step in the tangent space by applying the inner product. Now, if I make a long step, it will throw me to a different point on the manifold, and the tangent space will somehow rotate together with me. So I cannot anymore take two vectors on the manifold and add or subtract them. This is a meaningless operation. Okay?
It only means something when you are particularly close.
Exactly, infinitesimally close. But I will use this construction to define calculus. And then a very important conceptual step that we'll need to make in order to define calculus is to redefine all the notions as gradient, divergence, Laplacian, and so on, in terms of these local operations in the tangent spaces, rather than writing x plus dx. X plus dx is meaningless on the manifold. Okay? Yes.
So you allow for different inner products, and let's say if there is like some shape that we are accustomed to, like 3D shape, it's only the same inner product, but
okay. So it's a very important point. So first of all, I can equip the manifold with any Riemannian metric. Okay?
No, but one, no. You can have
one way a metric will be induced by the Euclidean. So if I'm thinking of a manifold as an embedded surface, as a surface, let's say a two-dimensional manifold in R3. So there is a metric, a Euclidean arc length, that operates in R3. This length structure induces a metric on the manifold. It's called, basically, it's induced by the connection of the ambient space. I can embed it in a different space and it will induce different metric. But in general, the Riemannian manifold can be equipped with any metric. And actually, any Riemannian metric can be realized as an embedded surface.
But only one, or can you have like subset of multiple different Riemannian metrics?
Well, again, a manifold is defined, so once
Yeah.
you fix the metric, it defines the
Ah,
metric.
okay.
Yes.
Sorry, going back to it, but there's something that is a bit secret about the argument. You're saying I can only define distance for points that are relatively close to each other, but how do you define points that are relatively close to each other through distance?
Okay. Well, I'm not going to define how I measure distances on manifolds because I'm going to define infinitesimal calculus. So I don't care about measuring long distances, but it can be done. You can describe a path on a manifold, and you can integrate, basically, you can make infinitesimally small steps, measure their length using the inner product. When you are infinitesimally small, you are staying within the same tangent space, and just integrate those small contributions over the
When you
path.
say infinitesimally small, we are talking about the regular Euclidean matrix in which the manifold lives.
Well, so if you have a problem with this, think of some parameterization domain in RD from which I'm mapping to the manifold. Okay, so I can measure a regular Euclidean distances in this domain. Of course, they will translate into some other distances on the manifold. Okay, but still there will be a continuous relation. So if I'm small in the parameterization domain, I'm small in the manifold. Okay. Again, I don't want to go into these details. I don't think we need them, but it can be rigorously defined. Okay. Okay. So once we have this structure, let's define two types of objects on manifolds. I will define what is called a scalar field. A scalar field will be just a function f from the manifold to R. It paints every point on the manifold with some number. Okay, think of, for example, of a temperature distributed on a surface. Okay, so it's a number attached to every point on the manifold. I will also define what is called the tangent vector field, or the vector field in general. That will be noted by capital F. It will be a map from so basically it will take a point on a manifold and map it to the tangent bundle. So essentially F at point P on the manifold is a tangent vector in PP. Okay? So it maps points on the manifold to tangent vectors in the corresponding tangent space defined at the point.
This is what you mentioned before about the small step.
Well, so basically, I will use the notion of vector fields to formalize or to generalize the notion of infinitesimal steps on manifolds. So you cannot add some just global vector to shift an argument of a function, because this operation is not defined on the manifold, but I can displace myself by a small amount by using this notion of a vector field. It will displace every point by some amount, but working in the local tangent spaces at every point. Okay? So these are the two objects that I'm going to define on my manifold. And let's now define, basically, let's build calculus on manifolds. So let's start with the definition of, so basically I would like to generalize this notion. Let's keep it in the same location. I would like to generalize this notion. Of course, this operation is not defined on the manifold. This is only defined in a linear space, but on the manifold we don't have a global linear structure, right? We have some local linear structure. So I will need to generalize this to manifolds. Okay, so we cannot write anything like this. So I would like to define the following operator. I will define, given a scalar field f, I will define what is called the differential operator, differential. The differential of this scalar field f, it will be a map from the tangent bundle to R. Okay? Now, how exactly I'm going to define this map? Well, it will take a point.
Don't
right?
you need a path for this?
Pardon?
You need a path or something.
No, so wait a second. So currently it's just an abstract operator. So the differential of f at point P on the manifold will take a vector v in the tangent space of P, and map it to some number, right? By means of a linear function. So basically I will write an inner product, of course, in the appropriate tangent space of vector v with some. Okay? So this is how I define a differential. Okay? Now this something, this object that is written here, needs to be a tangent vector. Okay? This needs to be a tangent vector. So I will construct, so basically it's a tangent vector at a point P. So let me write here, it is basically this thing is a tangent vector, is a tangent field, sorry, at point P. Okay? And now this object, this operator that takes basically, okay, let me do it. Let me do it differently. So basically, I need a field here, a vector field, to define this linear function. Okay? So basically, I will define a gradient. I will define the notion of a gradient that takes a scalar field and gives me a vector field. Okay? So for the purpose of defining it, let me construct two spaces. Basically, I will construct two Hilbert spaces, two inner product spaces. I will define two types of inner products. The inner product on this space, L2 on M. So basically, this is the space of all square integrable functions, all square integrable scalar fields on the manifold, and the inner product between them will be given by the integral on the manifold of Fp. Let's write F and G, Gp, dp, and dp is the standard volume form on the manifold that is induced by the metric. We can easily define it in terms of, basically in terms of the metric. This is the standard way of doing integration. Now, for the vector fields, basically this is the space of square integrable functions on the tangent bundle, right? Basically vector fields. I will define the integral. Now the vector field is a vector, right? So I will need to write an inner product between Fp and Gp, inner product on the tangent space at point P, again dp. Okay, so these are two standard inner products that I can define on scalar fields and vector fields. Okay? And I have basically this way I have these two Hilbert spaces of scalar fields and vector fields on the manifold. Now, once I have this definition, let's go back to this operator. I am defining the gradient operator that takes an object, a scalar field, and gives me a vector field. Okay? So you can think of the gradient as that. So the gradient of function f is the unique vector field that defines the differential via this linear function. And we know from the Euclidean case that the gradient gives us the direction of the steepest increase of the value of the function. So here as well, it will give us the steepest increase of the value of the function, but now the increase is defined locally in the tangent space. So at every point, I will have a tangent vector telling me in which direction the function changes the most. So just think of it this way. I have some level lines of a function painted on a manifold on a surface. Okay? I will map this to the local tangent space. I will produce these level lines here. Okay? And there will be some tangent vector that tells me the direction of the steepest increase. Okay? This tangent vector is called the gradient. Okay? And it is defined on the tangent space at every point. Okay? So it's a tangent vector. Tangent vector field. Okay? It's exactly an object here. This is called the gradient. Now, once I have the gradient, I can define its formal adjoint operator. Now, just remember what is an adjoint operator. An adjoint operator is defined this way. So I will take the gradient of f, and it will give me, so f is a scalar field. I take a gradient of the scalar field f, it gives me a vector field, right? I will take an inner product of this vector field with another vector field g. The inner product is defined on the Hilbert space of vector fields, and this should be equal to, let's say I would like to write an adjoint operator here, it should be equal to f, the adjoint operator acting on g, and the inner product is defined on the space of scalar fields. Okay, this should be true for every f. The scalar field and every g, the vector field. Okay? So this adjoint operator, basically I can write it as gradient adjoint, but it is called the divergence. The divergence is, of course, it has the domain and the codomain of the gradient slope, right? So it is a map from the space of vector fields to the space of scalar fields. Okay? Now, the gradient physically means the direction of the steepest increase, right? So it takes a scalar field and it maps it to a vector field. The divergence does exactly the opposite thing. It takes a vector field and it maps it to a scalar field. So if I interpret a vector field as the flow of some matter, let's say some liquid on the manifold, the divergence measures the net flow, the amount of net flow going through an infinitesimal sphere surrounding a point. Okay, so this is the physical interpretation. If the net flow is positive, I have a source. If it is negative, I have a sink. Okay, and if I have divergence 0, it means that basically whatever enters the sphere exits the sphere. Okay, it's called the divergence threefold. Okay, this is the physical interpretation of the divergence. So before we make a break, let me define one more operator, and this was the goal of this small excursion into differential geometry. So let me take the gradient. So the gradient is an operator from scalar fields to vector fields, right? So I give it as an input a scalar field, I get a vector field. Let's now operate with the divergence. Okay, by the way,
You assume it is no bounded?
say it again, please?
In this definition, you assume that the manifold is no bounded?
Yes. If I have a boundary, well, then I need to define something on the boundary. But I assume that the manifold has no boundary. Okay? Boundary will not change anything dramatically, but then I will have boundary conditions. And then there will be different notions of operators, let's say with Dirichlet or non and non. So one thing, I'm missing a minus sign. Okay, so just one minus sign is this. The divergence is the negative adjoint of the gradient. Okay? It should be the negative adjoint. So I would like to take, let me write it this way, I would like to take the adjoint of the gradient and compose it with the gradient. So remember, the gradient maps from scalar fields to vector fields. Its adjoint maps back to scalar fields. So this will be an operator from the space of scalar fields to the space of scalar fields. Okay? And I can write it, of course, as the negative divergence of the gradient. Okay? So this is an operator mapping scalar field to scalar fields, and this operator is called the Laplacian, denoted by delta minus the divergence of the gradient. Okay? Now, what will happen if I take the adjoint of this operator?
Same thing.
It will remain the same thing. So this operator is self-adjoint, which, if you think of it as a matrix, it is a symmetric matrix. Okay? Pardon?
Not unitary? No.
It's symmetric. Symmetric in the sense of complex transport. Okay? But we are working with real vector functions. So basically, this is called the Laplace. And basically, this was the goal for my construction. Now it is very easy to see that this operator is self-adjoint, it's symmetric. So I will just take a scalar field and operate on it with this gradient and write this inner product. Of course, this will be an inner product on the space of vector fields. Okay? Now I can move one of these operators with an adjoint to the other argument of the inner product. So I can get F inner product with gradient adjoint gradient F. And this is just the Laplacian, right? Or I can move this operator with the adjoint here, and I will get gradient adjoint gradient, which is the Laplacian of F with F. And of course this operates on the space of scalar fields. So you see, basically, I have this form, right? Meaning that the operator is self-adjoint, right? Because I can move now this here with an adjoint. So it means that Laplacian adjoint equals Laplacian. Okay? So we'll see a few other properties of the Laplacian in a second. So let's do a break, and now we'll repeat all these derivations more quickly for graphs. We'll do exactly the same. Forward to another type of non-Euclidean domains. One important comment that all the quantities that we have constructed on manifolds, basically gradients, divergences, and the Laplacian, all of these are intrinsic quantities. Basically, intrinsic in geometry means that all these quantities can be expressed entirely in terms of the metric. And this means that they are invariant to isometric transformations. So, for example, if I have this manifold and I have an ant living on this manifold, so the ant walks on the surface. She measures distances and angles on the surface using basically the structure of the inner products on tangent spaces. So if I now bend this manifold in some way, so formally it means that I am embedded differently in the surrounding Euclidean space. I am embedded differently, but I am not changing the metric, so it is still going to be the same Riemannian metric. Guys? Okay. So I transform it without changing the metric. All the quantities that are measured on the manifold, or all the intrinsic quantities, will remain unchanged. Okay? And quantities like gradient, like Laplacian, and all basically derived quantities, because they can be described entirely in terms of the metric, they will remain unchanged under such a change of the embedding. Okay? So this is the notion of intrinsic quantity as opposed to an extrinsic quantity, something that depends on the way the manifold is laid out in the embedding space. Okay? So again, our goal was to construct the Laplacian. You will see in the sequel, so we have basically a third ingredient in which we will use the eigendecomposition of the Laplacian to construct a non-Euclidean analog of the Fourier transform. So before we do this, let's see another type of non-Euclidean domain, and then the construction of the Fourier transform will be basically the same for manifolds and graphs. So let's talk about graphs. So I will limit my attention to undirected graphs. So let's construct a graph from the following objects. First, I will have a vertex set. So a vertex set, a graph has a certain number, let's say n vertices. Of course, a vertex can be any object, but this set is isomorphic to just the set of numbers from 1 to n. So let's, by convention, define the vertices as the numbers from 1 to n. Okay? Then I will define, so this is the vertex set. Okay? Then I will define the edge set. as the subset of the product V cross V. So it's a set of pairs of vertices. This is the edge set. Okay? And then I will define two weight functions. So one weight function will be a vertex weight function. Sorry, vertex weight function. I will call it A. Strictly positive weights. And then we have edge weight functions. Edge weight function, which will be non-negative edge weights. So essentially, I don't need the definition of an edge set. I can just put zero values here to indicate that. Basically, I write Wij equals 0 to indicate that I and j is not in the edge set. Okay? So basically, it can act as an indicator function for the edge set. Okay? And this tuple, so this tuple of V, E, A, and W is called a weighted graph. Okay? Now, one thing related to that being directed or undirected, I will assume that the edge set is symmetric, or basically the weights are symmetric, in the sense that Wij equals Wji. So if I represent W as an n by n weighted adjacent matrix, it will be a symmetric matrix. Okay? It means that if Ij or Ij belongs to E if and only if Ji also belongs to E. Okay? And this is called an undirected graph. So basically, directed graphs will cause many complications. For example, with the definition of the Laplacian, so we'll limit our attention only to undirected graphs. Now, on undirected graphs, I can define two types of objects. And again, I'm trying to develop this story just repeating what we did for manifolds. I will define a vertex field which will be a function, let's write it lowercase f, on the vertex set. Real valued function. So you can think of it as a vector on a vector in Rn. If we have n vertices, we basically have this n-dimensional vector representing a function, a scalar valued function on the vertices of the graph. And then we'll have an edge field, capital F, from the edge set to R. Okay? And for technical reasons that I'm not going to explain, we assume that Fij equals minus Fji. Okay? So if I represent F as an n by n matrix, it will be an antisymmetric matrix, unlike W. Pardon?
You feel like a mathematical field?
Well, it's basically a field is a way of saying a function of something non-Euclidean. Okay? Or something Euclidean as well. And scalar field, basically a field is just a function filling the space. It can have its codomain in some space. It can be space of scalars, can be space of vectors, space of tensors, doesn't matter. It's called field. Okay? So this is called an edge field, and these two objects, think of them as a discrete analog of scalar and vector fields and manifolds. Okay? So edges represent directions, vectors, and vertices represent scalar values, basically points. I will also define inner products. So basically, I will construct Hilbert spaces of vertex fields and edge fields. So an inner product on vertex fields. So you see, this is basically, this will be Hilbert space of square summable functions, square summable sequences, basically vectors on the vertices. Because the graph is a finite dimensional space, it's obviously square some rule, right? So I will define an inner product as simply the sum over I, AI, Fi, Gi. So you can now think of these AIs, these vertex weights, as a discrete representation of the volume form that we have in integration on the continuous domains on manifold. Okay, so this is a discrete representation of this integral. And for edge fields, we have the sum of Ij belonging to E, Wij, Fij, Gij. Okay? So this is again we reconstructed the standard inner products. We need inner products to define, for example, the joint. Okay. Now the next operator I would like to define will be a discrete analog of the gradient. Okay, so I will call it a graph gradient. A graph gradient will be an operator. Remember, the gradient took a scalar field and gave us a vector field, right? So now the gradient will take a vertex field and give us an edge field. Okay? And the way I'm going to define the gradient, it is a vertex field. It is an edge field. So I need to define it with two indices. So I'm taking a scalar field, giving it to the gradient, and as a result, I'm getting an edge field that is defined as Fi minus Fj. Okay? And now pay attention that Fj, the gradient at Ji is minus the gradient at Ij. So it automatically satisfies that problem. Okay? Now, if I define this gradient in this way, and I have inner products, I can define the adjoint operator. Okay? Or the minus adjoint of the gradient will be called the divergence. So it's graph divergence. So divergence is minus the gradient adjoint. It is an operator from edge fields to vertex fields. It can be obtained from basically from the formal definition of the adjoint. I will write it in explicit form. So the divergence of an edge field F. Now this object is a vertex field at point I. Will be given by 1 over AI sum over J such that Ij belong to the edge set. And again, I don't need really to write this if I stick to this convention. Wij, Fij. Okay? And as a small homework, just check that this definition of the divergence and this definition of the gradient are indeed the adjoint of the other, by just substituting this into the inner products and basically the definition of what it means to be an adjoint operator. Okay? Now, once I have the gradient and I have the divergence, I can define what's called the graph Laplace. The graph Laplacian, again delta, will be simply given by gradient adjoint gradient or minus divergence of the gradient. Of course, this is an operator from the space of vertex fields to the space of vertex fields. And I will write it explicitly. The Laplacian of the vertex field F at point I will be given by 1 over AI sum over J, such that Ij belongs to E, Wij, Fj minus F. Okay? So Fi minus it. By the way, in physics, the Laplacian is defined without the minus sign. Well, it's just a matter of convention. So basically, so first of all, again, as a small homework, just verify that when you combine these two operators, you get this. It's very easy. Just substitute these two definitions. Now, what is interesting about this form of writing the Laplacian is physical interpretation becomes evident. So what is written here is that the Laplacian is a weighted average, or let's write it differently. The Laplacian is the difference between the value of the function at the point I and its weighted average on the surrounding. So the same interpretation was true for manifolds. It was just taking the average on an infinitesimally small sphere surrounding the point. Okay? And this is the interpretation we also know from physics. So basically, this is the meaning of the Laplacian. It's some kind of weighted average, or difference between weighted average of the difference of the values of the function on the edges of one ring of a graph. Okay? Now, why say?
According to the definition, the gradient is F1.
And you also put the minus here.
Ah, okay, so
Okay.
there is
Minus the difference. Okay? That was my confusion in the beginning. Okay, so now if we write, it is convenient, basically, it is convenient to think of vertex fields as vectors, n-dimensional vectors, right? Now, the Laplacian will be just a linear operator acting from Rn to Rn. Now, if we write the weights of the graph as an n by n matrix W, the vertex weights as a diagonal matrix with AI to AN on the diagonal, and we also define what is called a degree matrix. Degree matrix D. It's a diagonal matrix with the sum of over J, so that I and J belong to the edge set of Wij, and by convention Wii equals 0. Basically, this is the degree matrix. It's a diagonal matrix with the vertex degrees on the diagonal. We can write the Laplacian. Let me write it. Pardon? Well, of course, it's the diagonal over I, right? So it's okay. It's the diagonal over I. So once we define it this way, the Laplacian can be simply written as A inverse times W times D minus W, right? Times D minus W. Because the sum of Wij times Fi is constant, right? So it will just amount to the sum of Wij's, which is D. And then we have Wij times Fj. When Fj now is not a constant, basically these are all the elements of the input vector. This is the example. Okay, so we can write the Laplacian this way. Just check that it exactly represents that expression that we wrote explicitly in coordinates. And different choices of A lead to different definitions of the Laplacian. If we choose A equals I, we get what is called the unnormalized Laplacian. It is simply D minus I. It's called unnormalized graph Laplacian. if we choose A to be the inverse of D, the inverse degree matrix, we get what is called the random walk Laplacian. It will be I minus. I'm missing. It's not I, of course. It's W. Sorry. Of course, it has to be W. Okay, must be W. Otherwise, where is W? It's W acting on F. So it is D minus W, of course. And here it will be D inverse W. This is called the random walk Laplacian. And the name random walk Laplacian is because this matrix can be thought of as a transition probability of describing random walks of the graph. It's actually a stochastic matrix, so it can be thought of as transition probabilities. So basically, there are different constructions. There are a few more constructions, standard constructions of Laplacians on graphs. For example, if the graph is built as a discretization of a continuous manifold, the choices of W and A will be derived from the metric, right? Or from some discretization of the metric. And actually there are theorems telling when we construct the Laplacian in this way, whether it will converge to the continuous Laplacian of the manifold, which is called also the Laplace-Beltrami operator on the manifold that we defined before. So it appears that some properties can be preserved, while necessarily others will not be preserved. Basically, some kind of a no-free lunch theory. Okay, but basically, what is important is that we can construct the Laplacian both on manifolds and on graphs. Okay. Now, once we have the Laplacian, let's do the following. So, just for convenience, I will be thinking of my domain as a manifold, but essentially everything that I will write now will be valid both for manifolds and for graphs, because it is essential to have inner products. We have inner products in both cases, and we have the Laplacian. Okay? So Laplacian is a linear operator, and this linear operator will admit an eigendecomposition. Okay? Now, I told you that the Laplacian is a self-adjoint operator, right? What does it mean? What is the implication of being self-adjoint, or think of it as a symmetric matrix, in terms of this eigendecomposition? Yes?
Real eigenvalues.
Real eigenvalues, okay, good. What else? What can you tell about the eigenfunctions, eigenvectors? Orthogonal, right?
Okay.
So, do I need to prove this, or is it obvious? I mean, this is a fact from linear algebra. We can easily extend it to functional analysis, basically, to the case of more general operators. But this is simple proof. Let's prove. So let's prove first of all. I would like to say a few properties. So first of all, that Fi is orthogonal to phi j for every I distinct from j. So this is fact number one. And then another fact I would like to say that lambdas are not only real, they are also non-negative. Okay? So the operator is positive semi-definite. Okay? And the operator basically, the fact that the operator is positive semi-definite, just remember how we constructed it. It was gradient times gradient adjoint. So if you think of this gradient as a matrix, we have D transpose D, right? So when you multiply D transpose D, we always get a symmetric positive semi-definite matrix, right? So basically this is the algebraic fact. But let's prove it formally. And then once we have it, we'll see how to construct the Fourier transform. Okay, so let's prove the orthogonality first. It's a very simple proof. So let's take lambda I distinct from lambda j. Okay? And let's evaluate this inner product. Lambda I, phi j. Okay? And of course the inner product will be the appropriate inner product either on scalar fields or on vertex fields, depending whether we operate on manifold or on graph. I will just not write it explicitly, it's clear from the context. So I'm moving my lambda here, okay? And what is lambda phi I? is the Laplacian of phi I, right? Here phi j. Now I'm moving this Laplacian here with an adjoint. But what is the adjoint of the Laplacian?
Itself.
It's itself, right? So this is a crucial property. This is the Laplacian itself. So I'm writing this as phi I Laplacian phi j. And what is the Laplacian of phi j? It's lambda j phi j. And I'm using the linearity of the inner product. So I will write this as lambda j phi I phi j. Okay? So let me subtract the right hand side from the left hand side, and I'm getting lambda I minus lambda j times phi I phi j. Okay, this quantity is non-zero because I told you that I have two different eigenvectors. Okay? And this has to be equal to 0, of course, because I subtracted the right hand side from the left hand side. So the only way this can be 0 is if this quantity is 0. Okay? Which is exactly what I wanted to show. Okay, so I have orthogonality. Of course, the length of an eigenvector is something arbitrary. We'll just fix it to the unit length. So then I have an orthonormal eigenbasis of the Laplacian. Okay? Now, what about positive or non-negative spectrum? So first of all, let me show that my operator is positive semi-definite. Okay, so I will take a field f and will compute the inner product of f with Laplacian f. This is called the quadratic form, right? Positive semi-definiteness means that this quadratic form is always non-negative, right? So let me write it as f inner product with adjoint gradient f. Move this adjoint with an adjoint to the first argument, which will become gradient inner product of gradient with gradient. Of course, this is an inner product on scalar fields. This is an inner product on vector fields, but it's obvious, right? Now, what is written here is a norm squared on this field of vector fields. And a useful property of the norm is that it is non-negative. Okay? So I have a positive semi-definite operator. Now, a positive semi-definite operator, I can always apply it to a function represented in my eigenbasis, right? So I will take my function f and represent it in the eigenbasis. Well, because I have an orthonormal eigenbasis, I can always write it like this. I can always write it like this: f inner product with phi I times phi I, right? Now, if I operate with the Laplacian on f and compute an inner product. Okay, let me first operate with the Laplacian on f. I will have the sum over I, f phi I, f phi I. Sorry. Laplacian phi I, which is lambda I phi I, right? And now I would like to compute this expression, the inner product of f with the Laplacian of f. So I will just need to substitute this expression in the place of Laplacian of f. I will have a sum over I phi f inner product with phi I, lambda I, again f inner product with phi I. Okay? And if I write it like this, it is lambda I and some non-negative expression, right? It's f inner product with phi I squared. Okay? So this has to basically, in order for and I know that basically this has to be a non-negative quantity, right? Because I proved that my operator is positive semi-definite. Now I choose f. It has to be non-negative for every f. So I can select an f that gives me exactly one non-zero coefficient here, and all the rest are zero. I will just select f to be phi I, right? So if I afford any of the lambdas to be negative, I will get a negative expression. So in order for this to be satisfied for every f, I necessarily have to have all the lambdas non-negative. Okay? So this gives me the non-negative spectrum of the Laplacian. Okay? So I have orthogonal eigendecomposition with non-negative spectrum. Okay? So basically, I can represent as I did here. Let me write it again. By the way, what are the eigenfunctions of the Laplacian in the Euclidean domain? Complex exponential, right? You can, for example, derive it easily in one-dimensional case, right? This will be just complex exponential. So basically, the Laplacian is a shift invariant operator, or better to say, translation equivariant. So basically, of course, it is also diagonalized by the Fourier transform. Okay, you can write it in frequency as pointwise product. So essentially, this eigendecomposition of the Laplacian that we did for non-Euclidean domains generalizes the eigenfunctions that we use, the complex exponentials that we use to define the Fourier transform. So if I now take a scalar field and I write it in this way, okay, so I'm writing it in the eigenbasis of the Laplacian. Okay, it is also called the harmonic basis. These are called harmonic functions because of the physical interpretation of the Laplace equation. So basically, these coordinates are called the frequency response of f, and the operator that takes a function that takes f to this sequence fi is called the Fourier transform. So essentially, the Fourier transform is a map from, okay, so if now I need to make a distinction between graphs and manifolds. So let's say I'm on a manifold, and you can easily extend it to graph. It maps a scalar field to a square integrable sequence. Okay? So this is called the Fourier transform. Okay? Basically, I define the Fourier transform, and the inverse Fourier transform, basically, this is called the analysis operator. We call this operation analysis, and the inverse Fourier transform will be just synthesizing the vector back in the standard basis. So basically, this is the inverse Fourier transform, right? I can think of it as F inverse F hat. Okay? And of course, the forward Fourier transform, the Fi's will be given by the inner products of F with the Fi's, right? Because this is an orthogonal basis. So I define the Fourier transform. So let's now make this final step for when basically we'll see how we use it next week. So the final step, let's again recollect what we had in the Euclidean case. In the Euclidean case, we could write a convolution of, let me write it as f and g. A convolution of f and g could be written as the inverse Fourier transform of the Fourier transform of f product with the Fourier transform of g. And basically, we could use this right-hand side as an alternative definition of what it means to apply Toeplitz operator, what it means to perform convolution. Okay? Now, we don't have this thing anymore in the non-Euclidean domain. We don't know how to define convolution. However, so if we take two signals, two fields, f and g, we can compute their Fourier transforms, and we can easily perform element-wise products, right? Element-wise products on sequences. It's a clearly defined operation.
Does it have the same complexity?
Pardon?
Does it have equal complexity?
Complexity to what?
Computational complexity.
Well, computational complexity of a convolution, if you apply full Toeplitz matrix, it's n squared, right?
Yes, and also
This is also n squared. Now, you can do Fourier transform using FFT on Euclidean domains. This property is lost.
it's
It's now it's n squared. Unfortunately. f of t in Euclidean domain is n log n, but there is no f of t on non-Euclidean domain. Okay. So basically, we can define this. We can define this. So let me write explicitly this expression. I have f decomposed into Fourier coefficients. Basically, these are the f I hats times g decomposed into its Fourier coefficients. These are the gi hats. Okay, and then I compose it back. I compose it back by writing this synthesis series. Okay? What I have is basically forward Fourier transform of f times forward Fourier transform of g inverse Fourier transform of the result. Okay? And let me just define this as the convolution of the two fields f and g. Okay? So previously, the left-hand side and the right-hand side in the Euclidean domain, so this is Euclidean case, and this is non-Euclidean. In the Euclidean case, I could define this, I could equivalently define it in frequency in the Fourier domain. In the non-Euclidean case, I don't have this. I can only write this in frequency domain. So I will define this element-wise product in frequency as the convolution of the two fields f and g. Okay? Now, we have this shift equivariance property in the Euclidean domain. There is no such a thing as shift on a non-Euclidean domain anymore. At least you cannot define it trivially. You can still define what is called parallel transport on manifolds, but it is a more complicated notion, and it still doesn't have all the properties of a regular shift. Once you have curvature, basically, there is no way to simply shift things on a manifold. And the same goes about graphs. So, for example, we don't have any shift invariant structure. It means that if we think of this operation as some filtering, basically some weighted sum of the values of the field around the point, when we move from one point to another point on the domain, the weights of the filter will change, and they might change dramatically. Okay. So there is no shift invariant structure, but still, at least in the frequency, it is analogous to the diagonal form of the Toeplitz operator we had in Euclidean domain. So basically, instead of defining convolution as a Toeplitz operator, we define convolution as a diagonal operator in the frequency domain. Okay? Yes.
Does this function has any interesting properties? Why define it?
Well, there are many. There is a wealth of features. Yes, on manifolds and on manifolds. So we'll see some of these properties. I will show you some interesting properties that justify why at all to use convolution on Euclidean domains, and the same properties will hold for non-Euclidean domains as long as we construct convolutions in this way. Okay. So basically, from this point on, constructing a CNN on a graph is straightforward, right? Our parameters will be these frequency responses in the Fourier transform defined in the non-Euclidean domain. So instead of constructing kernels in space, we'll construct their frequency responses in the Fourier domain. Okay? These will be our degrees of freedom that we will learn. Okay? Well, we take the domain assumed fixed, we construct the Laplacian, we decompose the Laplacian to its eigendecomposition, and now we can do this construction. The problem with this is that it takes n squared complexity. If you have a graph with billions of vertices, like Facebook, for example, this is clearly a no-go, right? N squared is too big. What we can do, I will show you next week, is that we can avoid this spectral definition at all. So we are still going to do the same, but we are not going to, so we are going to bypass the eigendecomposition. And the way to bypass it, you can think of some function of the Laplacian. So think of, for example, of a polynomial of the Laplacian. The polynomial of the Laplacian will result in some frequency responses here, right? Because polynomial of the Laplacian will amount to applying the same polynomial to the eigenvectors of the Laplacian. Now, if you take a modest degree in the polynomial, basically you are just multiplying the Laplacian with itself, let's say, 5 times. It's a sparse matrix. It works only on one rings, right? It has local connectivity. So in a big graph, it will still remain a sparse matrix, right? So basically you work with small powers of the Laplacian, maybe some rational functions of the Laplacian. You don't go to the eigendecomposition. You work locally. You might have a huge graph. It is still a manageable complexity. Okay? So we'll see this explicitly next week.